Welcome all to this 23rd lecture of Principles of Statistics. In the last lecture, we introduced MCMC methods, including Metropolis Hastings MCMC methods. And today I'm going to give you a couple of examples of proposal distributions that we can use for this MH MCMC. And then after this, we'll talk about non-parametric statistics, a short introduction to it, and then we'll end the course. So, as we were saying with MH MCMC, the art is to choose the proposal distribution, so the Q, and so as I was just saying, I'm going to give you two important examples of proposals Q. Okay, so let's begin with so-called PCN, or preconditioned Crank-Nicholson, and this is, by the way, an improvement on upon another proposal that is a more traditional one. So improvement upon the random walk proposal. Yeah. So I will talk about both in a sec. Okay, so let's begin then with the latter. So let's assume that we are on D dimensions. So if this capital theta is P, let's say, rather than D, sorry, then it is quite natural to sort of explore this space through a Gaussian distribution, right? So we're going to move from, say, the current point to another one according to this Gaussian. Yeah? So let's write this down more specifically. So it's natural to set then, so remember we called Sj the proposal at the jth step. And so it is quite natural to just say, well, maybe it is a value around this theta j, which is the current state of the Markov chain. And so then we're going to add a bit. So this delta is a small number of xi, and xi is a normal distribution with zero mean and some covariance matrix capital sigma. And so this is for some, as I just said, capital sigma p, and also for step size delta greater than zero. So I do sort of place this seed of saying, well, the step size is generally very small, yeah, or small enough. Well, if it is very, very small, then we won't move a lot. And so essentially a lot of the proposals would be accepted. And if we take delta to be quite large, then what will happen is that the proposed new states are going to be very far, and probably it is unlikely that they are accepted. And so it is really an art, how to fine tune this so that we have a good acceptance rate. Yeah. Okay. So then this is what we call the random walk. So this is, let's say, so this is a random walk proposal. And so this is, by the way, if we wish to write it as we were doing with a Q and Qt, then this is just a normal distribution centered at T with covariance given by this. Yeah. Okay, but PCN is a variation of this. So a superior variation is this PCN, in which we're going to propose as Sj something very similar, but different enough so that we get different properties. So we have 1 minus 2 delta and then the square root, and this is going to be multiplied by this theta j, and then for the covariance we're going to have 2 delta, yeah, and psi. Okay, so psi and delta are as above, and what we get by proposing this is that the proposal distribution is then normal with, you know, this 1 minus 2 delta and t. And then in the variance, you know, the square root will cancel out and we'll get this in here, right? So what is important about this? Well, what is important is that if this theta j actually is distributed according to a normal with capital sigma, and it is independent of psi, then we get that the new value will also be centered and yeah, it will be centered with covariance matrix capital sigma p. Okay, and so this, you know, in some sense, what it's telling us is that we completely preserve the structure of this proposal and of the you know, the distribution of the theta j. So remember, we're sort of interested, well, we're not interested, but it's good to build intuition upon conjugate models, and this is one of those. And so then we get this, you know, as I'm saying, this preservation of structure. So let me just make a remark about this. So this structure preservation so it has important properties. Although these are beyond the scope of the course, yeah? But I just want you to know that, you know, in addition to the usual random walk proposal, there is a superior one due to this structure preservation, yeah? Beyond the scope of the course, yeah? Okay. So let's, as I'm just saying, let's look at a particular case. So important example as well is, so let's consider, you know, as we were saying in the last lecture, you know, the M8 MCMC methods. You know, what we have in mind as a very, very crucial application is Bayes posteriors. And so consider Bayesian, so Bayesian, or the Bayesian posterior with prior given by this N0 capital sigma distribution. Yeah. Okay, so assume for simplicity in the following, assume that this is just the identity, this is for simplicity. And let's just define, or let's denote, you know, the log likelihood by this small ln theta. Yeah? So this is log, and then this is the likelihood. So then what we get, and this is something you should check, is that the Metropolis, the Hastings ratio is given by, it's going to simplify to the following, yeah? And you really should check this. So this is sort of part of an example from the last example sheet. It sort of isn't given the wording, but you should check, okay, as well. So this is the exponential of ln s minus ln t. Okay, so I don't want to spend time on the actual computations, because this is just you know, sort of arithmetic. So I will let you check it. But you know, the reason why I want to bring this up is because I want to make the following remark, and is that remarkably, what we've seen essentially is that if you have a Gaussian prior, and it doesn't matter what likelihood you have, but if you have a Gaussian prior, then we can sample or approximately sample from a general posterior by running a Markov chain that only requires computations of likelihood ratio tests. Okay, so this is what sort of comes out of this, the conclusion that comes out. So remarkably, for Gaussian priors, we can approximately sample from the posterior by, well, by simply, or by only computing likelihood ratio tests. Okay. Well, not tests, test statistics. Okay. Okay, so that sort of ends the first example, and now let me also talk about, so let me just underline this in this way. Okay, because it's not really a section. So then let me talk about Gibbs or Gibbs sampler, so-called. And this is, by the way, this was introduced separately. Okay, I'll say that in words, actually. So this was introduced separately to, Metropolis Hastings MCMC methods. And in fact, it is quite important in itself because there are several generalizations of it that really don't fit this MH MCMC sort of setting. Yeah. Okay, so what is the idea here for the proposal? Well, let's just go straight away to the proposal. And so so in the MH MCMC context, the proposal is specified through the following. So what is, what we're sampling? Well, we're simply sampling. So we're going to say that the mth element of the J+1 state of a Markov chain is going to be distributed, or we're going to sample it from, our distribution mu, which is the one we are trying to sample from. But we're going to take the conditional distribution. So let me just write this down. So we're going to take the conditional distribution of the mth coordinate. So this is basically an algorithm in which we're going to simulate coordinate by coordinate. And as I'm saying, what we want is this conditional distribution of this guy on the rest of guys. Okay, so that's m-1, and then the m+1 entry, and the last one, so say capital M of them. And in practice, for the J+1 element of the chain, we're going to, the conditioning is going to be given by the J+1, the first coordinate, up until, the same type of quantity for the m-1. But then there is a difference here, because we haven't sampled, if we're doing this sequentially, we haven't sampled the the m+1 entry for the jth step of a chain. And so then we're going to condition on what we have, essentially, yeah? Just these guys here. Okay, so this would be the how we sample this. So you may be surprised because I haven't written here the SJ or SJ plus 1. And so I'm implicitly stating that, that we always accept the proposal. Okay, so this is, something that one can show, and is that it can be shown, or indeed, it can be shown that so this Hastings ratio that we would need to compute generally is always 1. Yeah. So there is no sort of step 2, if you like, in the usual description of the MHMCMC that we had. Yeah. So no step 2. Yeah. Okay. Okay, so then let's move on now to the non-parametric methods. So let me start here. So for non-parametric, I guess methods or statistics, but we're only going to talk about a few methods. So let me briefly state, the idea of non-parametric statistics. And so as usual, what we get, or what we start with, is some data that we observe. We observe a sample, x1 to x small n, that is, IID according to some capital P. But, unlike before, like so far, what we have, regarding this P is the following, is that P will belong to a calligraphic P, or, or P has PDF lowercase f belonging to a calligraphic F space. And the important thing, the difference is, non-parametric to from parametric statistics is that these two spaces, possible spaces, let's see, so P and F have dimension equal to infinity. Yeah? So it's an infinite dimensional space. Okay, so then what we have is that we don't really have an index for the family, right? Like we did. So let me just write that. So thus, they're not, at least formally, they're not indexed by a parameter. And so this is the reason why we call, this area of statistics non-parametric statistics, or in this case, non-parametric. Let me just write from now on non-P, so non-P models. Yeah? Okay, but I mean, you could argue that you could still interpret the P and the F as parameters in themselves and other things as well, like the following. But, it's just a way of calling, non-parametrics is just a way of calling this sort of setting. Yeah? So by the way, in statistics and machine learning, we have a slightly different definition of non-parametrics. So for machine learning, non-parametric methods, the dimension is not really infinite straight away, but rather it will grow to infinity as we get more and more data. So in some sense, the dimension of a model depends on the number of samples, and it is allowed to go to infinity as, as the number of samples goes to infinity. Now, in statistics, we call that setting high dimensional statistics. Yeah? But that's just a matter of terminology. So we can start straight away within infinite dimensional space, and then in that case, for statisticians, we are within the realm of non-parametric methods. Yeah. Okay, so note, or maybe let's say, despite P and F can be interpreted as parameters, if you like, parameters themselves. Or, as I was saying, in many occasions, the P can actually be written as a, statistical model as we was writing it before, or the same for the calligraphic F. So we can write it as F theta, theta in some parameter space, but the difference with what we had before is the dimension of this guy will be infinity. Okay, so we could in some sense index this, yeah? Okay, so one of the advantages of non-parametric statistics is that we can avoid, strong parametric assumptions, and so we're going to see this now in the following. So, an advantage of non-parametric statistics, or let's say statistics, is that we, as I'm saying, so we can avoid strong parametric assumptions. Some people may say that they're not actually that strong, but there are different communities in stats, as you would expect, so parametric assumptions. And so this is one of the arguments for non-parametric stats. Because then, we're sort of avoiding some potential lack of identifiability. If you remember from the beginning of the course, the definition, then you should think about it. Yeah? So so potential lack of identifiability. Okay, so let's then, as I was saying, let's focus on the CDF for some time now. So we can estimate this capital F, so the usual CDF, and we're still in one dimension. So let's write P of X less or equal than T, and T in the real numbers. So we can do so directly. Yeah? Directly and only assuming it is a PDF. While before we were assuming, sorry, CDF. While before we were assuming that, whatever we are estimating is from a family of distributions with a given parametric assumption. So let me note, or to introduce an estimator, so noting that, so the definition of a capital F can be rewritten as the integral over R of the indicator from -infinity to T, and T included, and we integrate with respect to the P. And also, if you remember from Bootstrap and the last lecture, so a combination of concepts from both, is that this measure can be approximated by this empirical measure. Yeah. So let's write this as the sum of the sample average And in this case, it's not really sample average, but sample evaluation average, if you like. And this is a Dirac delta, so I spoke about this in the last lecture, and this is at X as well. And we define this as the Pn. Okay, so rather than P, this is Pn. So noting this, we can use the so-called empirical distribution function. Which is then given by Fnt and the gain, so this is with respect to this guy, Pnx. Yeah. And if we write this out, then this is just simply the sample average of these guys. So minus infinity t, xi, and this can also, sort of informally be written as the sum of the number of xi's that are less or equal than t, over n. Okay. So given this, we have the following result.